Okay, let's start lecture 7.7 on complex numbers. So just to get you a small introduction. So we're going to actually introduce a new number. So I'm drawing the number line, and the number line goes on to infinity and minus infinity. Of course, those aren't actual numbers. It just means it keeps going on and on and on, and there's no end to it. And if we want, we can put 0 right there and divide it right in 2. But all of the real numbers are there. Every last bit of this number line is occupied by a real number. There are no gaps. So if I could zoom in infinitely small, no matter how much I zoomed in, I'm going to find a real number. And that's really an amazing aspect of the real numbers. So if I'm talking about adding a new number, where is it going to go? There isn't any place for it to go because there's no space for it on the real line or on the number line. So that means any new number that I add is not going to be a real number. And that's exactly what we're going to do. We're going to introduce what are known as the complex numbers. So the complex number is a number written as the sum of a real number A, so A is a real number, and a multiple B of the imaginary unit I. So I is going to be the new number that I introduce. And you say, well, what makes it a number? Well, because I can do everything with I that I can do with the real number. I can multiply it, I can divide it, I can add it, and I can subtract it. So it has all of those properties. So a complex number has two parts. It's written as A plus B times this new addition to our number system, which is I, and this is called the imaginary unit. And this is a complex number. So let me give you an example. 1 plus 5i. That's a number. This is the real part, and this is the imaginary part. And every real number has that. Notice there are no restrictions on A and B. It's possible for A to be equal to 0, and it's possible for B to be equal to 0. Let's consider this last part. If B is equal to 0, then we just have the regular real numbers, since A plus 0 times I is just equal to A, because 0 times I is still 0. So if you want to see it written out, that's A plus 0, which is equal to A. And A, by definition, is a real number. So A and B are both real numbers. So what is this new I? What properties does it have? Well, the easiest way to do that is just to define it. So we're going to define I. What is I? Many times in math, to define something, we'll put two dots and then an equal sign. That means by definition it is equal to. But I'm going to fill in this blank over here secondarily. The easiest way is not to define I, but rather to define I times I, or I squared. And I squared, by definition, is equal to minus 1. And that should make it clear to you that I squared, that I itself cannot be a real number, because any number multiplied by itself is always positive or 0. 0 times 0 is 0, If I start out with a negative number, like minus 3 times minus 3, which is minus 3 squared, I always end up with a positive number, always. So whatever this I is right here, when I multiply it by itself, and just so you're clear, I squared means I times itself. I end up with a negative number. So there's no real number with that property, so just by that definition in and of itself, you know it's not a real number. That's one possible way to do it, and if we start out this way as our definition, it follows then that I itself, when I take the square root of both sides, is equal to the square root of minus 1. So sometimes they define I as being the square root of minus 1, and then square it, and we get I squared is equal to minus 1. Sometimes we start with I squared is equal to minus 1, and then we derive I is equal to the square root of minus 1. I think for you guys, it might be most helpful if you just remember that I squared is equal to minus 1. I think that's going to be the most helpful. And then once you have that, you can take the square root of I squared, and the square root of I squared allows me to bring the I outside of the radical and get I is equal to the square root of minus 1. So here's the thing, square roots and their products. So the familiar root of square roots of products now extends to the complex unit I. So I is the complex unit, or if we want to be more precise, it's the imaginary unit. It's the number that we just added to the real numbers. So let's look at this. So let A be a real number. So the square root of minus A is equal to the square root of A times minus 1. But minus 1 is equal to I squared by definition. So since I squared, and the index here is 2, that allows me to move the I outside of the radical sign. So notice here, the I is on the outside of the radical sign, and customarily we put it at the beginning of the radical sign, which to me I don't like, because I just told you that our complex numbers are written as A plus BI, where B is a real number. So when I write I on the square root of 2, I'm writing it as A plus I times B. But we really shouldn't be too worried about that, because B times I is the same as I times B. It shares all of the properties of the real numbers, and this is the commutative property. Just like 5 times 3 is equal to 3 times 5, 5 times I is equal to I times 5. So let's write this in I notation. So we can just take this as a proof. If A is a real number, and such that minus A is negative. So if minus A is negative, that means A itself has to be positive. So if I have the square root of a negative number, I can just immediately say that's equal to I times the square root of A. Sorry, when I highlighted it there, you lost that sign. So that's exactly what we're going to use. That is the proof right there. That's how that's derived. And we're going to go ahead and use that right now. So the square root of minus 36. Well, minus 36 is less than 0. So by our theorem, that's I times the square root of 36, which is equal to I. The square root of 36 is times 6, and we normally write that as 6 times I. So again, I have the square root of a minus number, of a negative number. Well, by my theorem, that's I times the square root of the number without the negative sign. And we cannot simplify that any further, but I think it's more consistent to write that, since the square root of 5 is a real number, is to write that as the square root of 5 times I. Just be careful and make sure that the I is not underneath the radical. In other words, if I had written this, no, that's too, if I had written the square root of 5, and instead of writing I out there completely, accidentally shove it underneath the radical, then this is wrong. So keep that in mind. I have no idea what my math lab might want you to do. So here, we're going to do this just a little bit differently. This is minus the square root of minus 20. So that's minus the square root of minus 20. Well, that's minus. Well, this is the square root of negative number, so I bring out the I, and that's just the square root of 20. I'm not done yet, but I can go ahead and remove the parentheses if I want and say that's minus I times the square root of 20, but I'm not going to do it just yet, because there's something I can do to simplify the square root of 20. The square root of 20 is the same as the square root of 4 times 5. And 4 is equal to 2 squared. So that's minus I times the square root of 2 squared times 5. So the index here is 2. That allows me to bring the 2 out, 2 squared out. It just becomes 2. It loses its exponent. And now at the last step, if you want, you can go ahead and apply the negative. This is the negative of this quantity, so we just remove the parentheses. It's minus 2I times the square root of 5. Oh, I guess we need to go on down. So now let's go ahead and we have to multiply and divide. So here again we have to be really, really careful. There is a theorem way back on page 433 that we cannot use. That theorem says that if you have the square root of a times the square root of b, the theorem states if a and b are real numbers, I'm just being lazy today, then the square root of a times the square root of b is equal to the square root of a times b. And here you have to pay very close attention, because they have to be real numbers. So I can't use this theorem when I'm talking about the square root of minus 3. Because the square root of minus 3 is the square root of 3 times I, and that is not a real number. In other words, not only do I introduce I, and that's not a real number, but any multiple of I. So if I let a be any real number, and I multiply a times I, that's not a real number either, because it's a multiple of this thing, which we call the imaginary unit, which is not a real number. So let's do this the correct way. All we have to do is follow the exact steps that we did above. So let's do the square root of 3 minus 3. times the square root of minus 5. Well, the square root of minus 3 is I times, I'm going to do this, I'm going to put the real part always first, is the square root of 3 times I. And the square root of minus 5 is the square root of 5 times I. So now I'm multiplying them together. Now notice 3 and 5, the square root of 3 and the square root of 5 are both real numbers, so I can use the theorem. So this is the square root of 3 times 5, and I times I is I squared. So that's the square root of 15, and I squared by definition is minus 1. So this is minus the square root of 15. So this is a really important example. Make sure you understand this. I'm losing my voice early today. I apologize. We'll just get through it. Okay, let's do 2b. So the square root of minus 36 times the square root of minus 1 is equal to the square root of 36 times I times the square root of 1 times I. Well, that's the square root of 36, which is 6, and that's times I. And the square root of 1 is just 1, and 1 times I is I. So that's 6 times I squared. But I squared is equal to minus 1, so that's minus 6. To C. So we're going to do the square root of minus 125 times the square root of 5. So we don't have a quotient rule we can use right here. We could extend it, but we've not been given the quotient rule yet. So let's factor 125. 125 is obviously divisible by 5. When I divide it by 5, I get 25. And 25 is 5 times 5. So 125 is 5 cubed. So that's going to be the first thing we're going to do, is minus 5 cubed over the square root of 5. So I'm going to go ahead and simplify the first. That's going to be the square root of 5 cubed times I. Because 5 cubed is positive, and when I negate it, it's negative, over the square root of 5. Well, we're getting closer. From the rules that we've used earlier, the square root of 5 cubed is the same as 5 squared times 5. Now all of that's multiplied by I. So all I've done right there is I've rewritten the numerator. I've not done anything with I, but I've rewritten 5 cubed as 5 squared times 5. And this is still over the square root of 5. Let's go ahead and simplify. Well, I have my division line. The square root of 5 squared times 5, by what we've learned previously, it's not wanting to turn off, is 5, because I can take the 5 squared out. So over here on the side, just as a quick reminder, 5 squared times 5, my index is 2, so that allows me to pull that out. So it's the power 2 divided by the index times what remains, and 5 to the 2 divided by 2 is 1. That's 5 on the square root of 5. divided by the square root of 5 times I. Now the square root of 5 divided by the square root of 5 cancels, so all I have is 5 times I. Okay, so just get used to it, and we're going to keep this pretty basic. In particular here. So I give you a formula to add and subtract. So like I said, the complex unit I is a new number. It's not a real number, but it shares all of the properties of numbers. That means we can add them and subtract them, multiply them, and divide them. And the division, we're only going to do one example, and we're going to keep everything else pretty straightforward. So I actually tell you what to do. You add and subtract the real parts together, and then you add and or subtract the imaginary parts together. So in this case, you can literally treat the I as if it were a variable. So you gather like terms, pretty much the same. If you keep that idea in mind, you'll do really well. So here, let's go to white. 3a. So we're going to add 2 plus 3i, and we're adding it to minus 3 plus 2i. So what do? We gather the like terms. The purely real numbers are 2 and minus 3. We add those. And then we add 3i and the 2i. So 2 minus 3 is minus 1, and 3i plus 2i is equal to 5i. So just so you can see by analogy, 2 plus 3x plus minus 3 plus 2x. Same exact principle. You go 2 minus 3 plus 3x plus 2x, which gives you minus 1 plus 5x, and in this case our x is I. So this is the exact same principle. Notice I'm not telling you to replace I with x. I'm just telling you that collecting like terms are exactly the same, except in this case these are pure real numbers, and these are multiples of the complex unit or the imaginary unit I. Five minus 1 minus I. So just like anything else, we're going to simplify this. This is 5. Minus 1 times 1 is minus 1. Minus times minus is plus. So that's equal to 5 minus 1 is 4. Minus 3 minus 7i minus a minus 6. Well, minus 3 minus 7i. A minus is a plus 6. So I'm going to gather together the real parts of the complex number and then put the minus 7i by itself. 6 minus 3 is 3 minus 7i. To subtract them, we're going to be doing the exact same thing. So I just subtracted one. Let me make up one more. I want to give you, see, this is a subtraction. We actually did one addition and 2 subtractions, but I'm not satisfied with this. Let's do one more example. So I'm just going to make it up. 3 plus 8i minus 7 minus 4i. So this is 3 plus 8i. Nothing's going to change there. But minus 7 minus 4i, just treat that as multiplying each term as a negative. So that's minus 7. Minus times minus gives me a plus. Now let's put together the real parts, which are 3 and minus 7, and put together the complex parts. So 3 minus 7 is minus 4, and 8 plus 4 is 12. And that would be your answer. Now here I give you just this terrible, terrible formula. It looks so freaking complicated. Just ignore this. We're going to multiply complex numbers exactly like we would be multiplying binomials. You can FOIL them or you can break them apart, either way. And I think it's just better that I show you how this is done. In one case, it's really, really simple. So here are two multiples of the imaginary unit I. So this is 4a. So I have 7i times 3i. Well, that's 7 times 3 times I. Well, 7 times 3 is 21, and I times I is I squared. But remember, I squared is equal to minus 1. So this is 21 times minus 1, which is just another way of saying minus 21. I thought I had everything turned off. So 3i times 2 minus I. Again, distribution. All of the properties of the real numbers hold. So I'm going to take my 3i and multiply it by 2, and take my 3i and multiply it by minus I. So this is equal to 3i times 2. Well, 2 times 3 is 6. That's 6i. And then I do minus I times 3i. Or if you want, you can write it as 3i times minus I. Well, that's 6i times minus 3 times I squared. So the minus I times 3i is minus 3 times I squared. But you have to remember that I squared is equal to minus 1 for the upteenth time. So that's minus 3 times minus 1. So the end result is rather surprising. It's 6i plus 3. And our last example, 2 minus 5i times 4 plus I. I'll do this two ways. I'll use the FOIL method, first, outer, inner, last. So my first are my 2 and my 4. 2 times 4 is 8. My outer is 2 times I, so it's plus 2i. My inner is minus 5i times 4. That's minus 20i. Remember, just treat the I as if it were an x, but you got to be careful because x squared is minus 1 if you're doing that. And then I do the last. That's minus 5 times I. That's minus 5i squared. So that's 8. 2i minus 20i is minus 18i. And minus 5 times I squared is minus 5 times minus 1. So I squared is a real number. So that's 8. Minus 5 times minus 1 is plus 5. Minus 18i. And this gets me 13 minus 18i. So there's one method. We'll do it the other method. Both are good. Some of you might be using this method. I do. Depends on what mood I'm in. That's equal to, I take my first number and I multiply it by my second binomial. Then I take the second term and my first factor together with its sign and multiply it times my entire second factor. So now it's just distribution. You're going to get exactly the same thing. 2 times 4 is 8. 2 times I is plus 2i. Minus 5i times 4 is minus 20i. And minus 5 times I is minus 5i squared. And that's exactly what we had up here in this step right here. So of course it's going to go ahead and simplify to 8. 2i minus 20i is minus 18i. And minus 5i squared is minus 1. That's 8. Minus 5 times minus 1 is plus 5. Minus 18i. And this is equal to 13 minus 18i. Of course, the exact same number that we got here. Again, a terribly nasty formula I don't want you to memorize. This, however, I do want you to memorize. Let's actually look at the difference of perfect squares factorization. So this is something you absolutely need to be aware of. I'm sure you'll see it appear on the final exam more than once. A plus b times a minus b is a squared minus b squared. So now let's replace b with I. A plus I times a minus I is a squared minus I squared. But that's a squared minus a minus 1, which is a squared plus 1. So in general, if we have a, this time using a multiple, b of I times a minus bi, that's equal to a squared minus b squared times I squared, which is equal to a squared minus b squared. I squared is what? Minus 1. So that's a squared plus b squared. Now I'm just going to do one simple problem here. We just finished redoing the objectives for this class, and this was either minimized, dividing, or completely removed. And when an objective is completely removed, that means if the instructor does it, it's optional, it's up to them. So 2 plus I, all I'm going to do is 1a, 1 minus I. So what I'm going to do is I have to transform this. Now I'm going to transform it by multiplying it by 1. Now, for any complex number that's not 0 divided by itself is still equal to 1. So what I'm going to do is I'm going to look at this denominator, and I'm going to keep the real part the same, but I'm going to change the sign on the imaginary part. And whatever I put in the denominator goes in the numerator. 1 plus I divided by 1 plus I is still 1. So I've not changed the quantity. So this is 2 plus I. Now it's just regular old multiplication of fractions. So let's work on the bottom. 1 minus I times 1 plus I, by what I just showed you, is 1 squared plus minus 1 let's do it over here. Well, that's 1 squared minus I squared. 1 squared is 1, but I squared is minus 1. So it's 1 plus 1, which is equal to 2. Now we can FOIL the top. 2 times 1 is 2. 2 times I is plus 2I. I times 1 is just 1I. And I times I is I squared. So let's go ahead and simplify. I squared 1 squared. I've already done it right here. So I get the denominator is equal to 2. So that's 2. 2I plus I is 3I. And plus I squared, well, I squared is minus 1. So there's a I there, sorry. So 2 minus 1 plus 3I in the numerator over 2. So that's 1 plus 3I over 2. Now, my math lab may actually want you to write this as in the form A plus BI. So that's equal to, remember, A plus B divided by C is equal to AC plus BC. So this is 1/2 plus 3/2 I. And that's A plus BI, where A is equal to 1/2 and B is equal to 3/2. And then the very last thing is finding powers of I. So here I give you a theorem. I cubed is equal to minus 1. It's a really easy proof. I cubed is equal to I squared times I. But I squared is equal to minus 1. So I squared times I is minus 1 times I. So I cubed is equal to minus I. So we have the following rule I'm going to add. I'm just going to declare that I to the 0th power is just like anything else that's going to be equal to 1. So we have the following. I to the 0th is equal to 1. I to the 1st is just equal to I. I squared is equal to minus 1 by definition. And I cubed is equal to minus I. I just proved it right there. So what about I to the 4th? Let's figure out what I to the 4th is. Let's see about this. So I to the 4th is equal to I squared times I squared. But I squared is minus 1. So minus 1 times minus 1 is 1. So I to the 5th is equal to I to the 4th times I. But I just found out that I to the 4th is 1. So that's 1 times I. So that's just equal to I. I to the 6th is equal to I to the 5th times I. But I just discovered I to the 5th is equal to I. And that's times I again, which is I squared, which is minus 1. and I to the 7th is equal to I to the 6th times I, which is minus 1 times I, which is equal to minus I. Notice that the pattern repeats. 1I minus 1 minus I, 1I minus 1 minus I. So here's the trick. We want to find powers of I. So with the exception of the last one, here's what we're going to do. I have I to the 7th. Well, clearly, this pattern repeats every 4. So what I do is I divide 7 by 4. Goes 1 time, 4, 3. My remainder is equal to 3. So this is the same as I to the 3rd. And I to the 3rd is equal to minus I. You might say, how did I get that? Well, let's do it. 7 is equal to 4 times 1 plus 3. So I to the 7th is equal to I raised to the 4 plus 3, which is the same as I to the 4th times I to the 3rd. But I to the 4th is equal to 1, and I to the 3rd is equal to minus I. So I get minus I. So all we have to do is, if the numerator is not negative, all we have to do is divide, let me say this again. If the power of I, the exponent attached to I, is not negative, then all I do is find the remainder on division by 4, and it becomes I raised to the remainder of division by 4. So I to the 20th. Well, we know that 20 is evenly divisible by 4. Remainder is equal to 0. So that's equal to I to the 0th, which is equal to 1. Let's do I to the 46. So we come over here and divide 46 divided by 4. As remainder 2. So this is the same as I squared, which is minus 1. What about this last one over here? I don't know what that one even does. I to the minus 12. Well, what we want to do is write minus 12 is equal to I to the minus 12 is equal to 1 over I to the 12th. So what we do, 1 over I to the 12th, and that's equal to, well, what's 12? That's 1 over I. Is 12 divisible by 4? Yes, remainder is equal to 0. So that's 1 over I to the 0th, which is equal to 1. So what you do is, that's one way to do it. There are other ways to do it, but I like using the fact that a to the minus n, if that's a number like x to the minus 16, is equal to 1 over x to the 16th. My math lab or the book does it slightly different. I can't quite remember right now how they do it, but we can just use this and it should work out. Like I said, for the most part, finding powers of I, we're going to concentrate on examples A, B, and C. And I believe that is it for, that's it for Chapter 7.